The year is 1943. In the frantic, smoke-filled strategic offices of World War II, a question of life and death hung heavy in the air. A question that wasn't about bullets or bombs, but about a far more elusive enemy, human perception itself. Military commanders faced a grim dilemma. Their vital bomber fleets, returning from perilous missions over enemy territory, were often riddled with bullet holes. Engineers meticulously mapped the damage, patches of torn metal across the wings, the tail, the fuselage, each telling a brutal story of combat. Their logical conclusion, it seemed, was obvious: reinforce the areas that had been hit most frequently. But then, a brilliant Hungarian-American mathematician, Abraham Wald, working for the Statistical Research Group at Columbia University, offered an insight so profoundly counterintuitive, so utterly revolutionary, it would rewrite the rules of aerial warfare and save countless lives. Wald's perspective shattered their initial assumptions. He did not focus on the planes that returned to base, the ones sitting before them, scarred but triumphant. Instead, he posed a chilling question: what about the planes that didn't return? The bullet holes on the surviving aircraft, Wald argued, were a deceptive map. They marked the spots where a plane could be struck and still endure the journey home. The true vulnerability, he revealed, lay precisely in those areas with no damage at all: the powerful engines, the vital fuel tanks, the cramped cockpit housing the pilot and crew. Because if a plane was hit in one of those critical zones, it simply never made it back. The damage they observed was not a blueprint of weakness, but rather a chilling testament to survivable injury. This profound observation illuminated a powerful cognitive illusion, a pervasive trick our minds play on us, known as survivorship bias. It is a systematic overestimation of success, born from our inherent tendency to focus exclusively on the triumphant survivors, while completely ignoring the vast silent majority of failures, the untold stories of those who vanished. We see only the planes that completed their mission, their damaged frames a misleading beacon of resilience, never truly acknowledging the hundreds, perhaps thousands, that simply ceased to exist in the vast expanse of the sky. This fundamental flaw in human judgment permeates and distorts our understanding of the world in ways we rarely comprehend. Consider the celebrated narratives of college dropout billionaires. Media outlets around the globe glorify these exceptional individuals, painting their unconventional path as not just viable, but often a superior route to monumental success. Yet, for every one of these titans of industry, hundreds of thousands, perhaps even millions, of other aspiring dropouts struggle, their dreams unfulfilled, their financial futures uncertain, their stories untold, and their failures unseen. We champion the survivor, internalizing their improbable journey as a blueprint for our own aspirations, inadvertently overlooking the colossal statistical wasteland of those who did not make it. The same insidious bias distorts our understanding of true risk in the volatile landscape of financial markets. We frequently hear triumphant tales of the audacious investor who made a fortune on a volatile, high-risk stock, their success amplified by headlines and financial gurus. What remains largely unheard are the countless others who risked everything and lost it all on identical gambles. In the crucial realm of medical trials, we might focus with intense hope on the handful of patients who respond miraculously to a revolutionary new drug, their dramatic recovery becoming the focal point of discussion, inadvertently downplaying the substantial majority for whom the treatment was either entirely ineffective or, in some tragic cases, even actively harmful. Survivorship bias crafts a subtly distorted reality, a hall of mirrors where only the lucky, successful few are ever truly reflected. This pervasive psychological principle, deeply embedded within our very cognitive architecture, constructs a peculiar and often dangerous reality for the survivor. It instills in them a feeling of being uniquely skilled, perhaps blessed by an unseen hand of fortune, or even fundamentally invincible to the perils that beset others. This feeling, this unshakable sense of continued existence against staggering odds, bears an eerie, almost unsettling parallel to the subjective experience proposed by the enigmatic concept of quantum immortality. To truly grasp this inherent vulnerability of our perception, to understand why our brains are so readily susceptible to such an insidious error in judgment, we must turn to the groundbreaking Nobel Prize-winning work of psychologists like Daniel Kahneman. His pioneering research into cognitive biases has illuminated precisely how our minds instinctively construct narratives of improbable survival, often even when confronted with overwhelming, contradictory evidence. Long before we delve into the bewildering realm of quantum mechanics, long before we entertain cosmic theories of parallel universes where every possibility is realized, our own minds are already pre-wired to construct this very narrative. This deeply ingrained psychological tendency serves as a fundamental blueprint for a grander, perhaps terrifyingly real, cosmic version of the same idea. It forces us to confront a profound and deeply unsettling question, one that resonates from the very depths of our being. Is our persistent, subjective feeling of continuous existence, of always navigating life's relentless and unavoidable catastrophes, a subtle, profound hint of underlying physics, or is it merely the ultimate, most personal expression of survivorship bias, playing out on the grand, improbable stage of our own lives? The grim calculations of survival bias, uncovered in the heat of a global war, revealed a profound, almost unsettling flaw in our perception. But what if this flaw, this persistent feeling of being the fortunate survivor, was not merely a trick of the mind, but a profound echo of the universe's deepest secret? To seek that answer, we must journey back, not to the battlefields of the Second World War, but to the hallowed, ivy-clad halls of Princeton University in the year 1957. Here, a brilliant yet deeply troubled graduate student named Hugh Everett III was about to propose an idea so audacious, so profoundly unsettling, it would forever challenge our understanding of reality itself. Everett was frustrated, almost tormented, by what he saw as the fundamental paradoxes at the heart of quantum mechanics, specifically the dominant Copenhagen interpretation. This prevailing view, championed by the towering figures of quantum physics like Niels Bohr, asserted that quantum particles existed in a hazy superposition of all possible states until they were observed. It was the act of measurement itself, the very act of looking, that forced the elusive wave function to collapse, crystallizing one specific outcome from a cloud of possibilities. For Everett, this was an inelegant, almost magical intervention, a subjective loophole that felt unscientific, a universe that only became real when we bothered to look. He sought a more universal, more objective solution, one that didn't depend on a mysterious collapse. His doctoral thesis, a radical departure from the established orthodoxy, was fiercely championed by his advisor, the visionary physicist John Wheeler. Wheeler saw the audacious brilliance in Everett's work, a mathematical elegance that promised to resolve the quantum mysteries without resorting to a subjective collapse. Yet, when Everett traveled to Copenhagen for a fateful meeting with the patriarch of physics, Niels Bohr, his revolutionary ideas were met not with debate, but with cold, almost dismissive indifference. Bohr, firmly entrenched in his Copenhagen interpretation, found Everett's proposal too outlandish, too philosophically uncomfortable to seriously entertain. This rejection left Everett isolated, his groundbreaking theory largely ignored by the mainstream for decades. Everett's relative state formulation, later popularized as the many worlds interpretation, or MWI, proposed a breathtakingly simple yet mind-bending alternative. What if the wave function never truly collapsed? What if, instead, every single quantum measurement, every fleeting interaction at the subatomic level, didn't just pick one outcome, but rather splintered the entire universe into multiple, non-communicating branches? In this infinitely branching cosmic tree, every single possible outcome of every quantum event would be realized in its own separate, equally real world. This was not a collapse of possibilities, but an explosion of realities. Consider the infamous thought experiment of Schrödinger's cat, a grim scenario designed to highlight the absurdity of the Copenhagen interpretation. A cat is placed in a sealed box with a vial of poison connected to a quantum trigger. If a single radioactive atom decays, the poison is released, and the cat dies. If it doesn't decay, the cat lives. According to the Copenhagen view, until the box is opened, the cat is both alive and dead simultaneously, a superposition. But for Everett, the solution was far more literal, far more profound. When that quantum trigger fires, or fails to fire, the universe itself divides. In one branch, the atom decays, the poison releases, and the cat dies, observed by a grieving scientist. But in an equally real, non-communicating parallel branch, the atom does not decay, the cat lives, and a relieved scientist observes its survival. The cat is never truly both alive and dead. Instead, two distinct universes come into being, each with a definite, singular outcome. Everett's later life, largely away from the academic physics he loved, saw him applying his unique mathematical insights to game theory, a field of strategic decision-making, and perhaps most chillingly, to nuclear strategy during the Cold War. In a realm where every single outcome truly mattered, where a wrong calculation could mean global annihilation, Everett's abstract understanding of branching probabilities found a terrifyingly concrete application. His work in this area, though far from the public eye, underscored his deep conviction in the mathematical precision of his ideas, a precision that could model not just the fate of a quantum particle, but the potential fates of entire civilizations. The elegance of his proposal lies in its mathematical fidelity. It takes the equations of quantum mechanics, the very bedrock of modern physics, and interprets them directly, literally, without adding any external, arbitrary rules like the collapse. But this elegance comes at a profound philosophical cost. Whatever its many worlds interpretation implies is an infinitely branching reality, a cosmic tapestry woven from every conceivable possibility, no matter how remote, how terrible, or how wonderful an outcome might seem. It is made real somewhere. This is no longer just a quirky thought experiment for physicists. It is a direct, undeniable consequence of a literal reading of the equations that govern our universe, a cosmic framework that transforms the abstract probabilities of quantum mechanics into a concrete, endlessly branching map of all that could ever be. Ancient Greek sailors, with their weathered hands and sun-baked faces, once wrestled with a profound philosophical paradox as old as their legendary ships. If the planks of a vessel were slowly replaced, one by one, over centuries, until not a single original piece remained, was it still the same ship? Was it still the ship of Theseus? This ancient riddle, debated by philosophers for millennia, strikes at the very heart of identity, permanence, and what it means for something to be itself. But what if this is not just a thought experiment for wooden ships and historical artifacts? What if this same existential challenge applies, not to a vessel navigating the Aegean, but to the very core of your being, the observer, navigating existence? The grand concept of quantum immortality, a breathtaking notion that suggests your conscious experience might always persist, hinges entirely on the continuous existence of a singular, stable observer. It posits that no matter how the multiverse branches, how reality splinters, you, the perceiving consciousness, will always find yourself on a timeline of survival. But this premise demands a radical question. Who, or what exactly, is this observer? What is this unwavering I that supposedly persists through every cosmic catastrophe? In the 1960s, groundbreaking work by neuroscientists Roger Sperry and Michael Gazzaniga delivered a scientific bombshell that rocked this very assumption of a unified self. They studied patients who had undergone a radical surgical procedure to alleviate severe epilepsy, a procedure that severed the corpus callosum, the thick bundle of nerve fibers connecting the brain's two hemispheres. What Sperry and Gazzaniga discovered was astounding. They found that these split-brain patients exhibited two distinct, often contradictory, centers of consciousness, each operating independently within the same skull. The left hemisphere, typically dominant for language, would often construct a plausible, but entirely fabricated, narrative to explain actions initiated by the right hemisphere, actions of which it had no direct knowledge. It was an interpreter, weaving a coherent story after the fact, making sense of what the self was doing, even if that self was fundamentally fractured. This was like two separate operating systems running on the same computer, but only one had the microphone and speaker, constantly making up reasons for what the other was doing. This suggested our feeling of unified selfhood is not a fundamental truth, but a brilliantly constructed story. This revolutionary insight paved the way for philosophical models that further challenged the notion of a single, central you. Consider the work of philosopher Daniel Dennett, who in his 1991 book Consciousness Explained, proposed the multiple drafts model. Dennett argued that there is no singular Cartesian theater inside your head, no single screen where you watch the world unfold, no central command center where all sensory input converges into one unified experience. Instead, Consciousness, as Dennett posited, is a chaotic pandemonium, a cacophony of parallel processing streams, constantly analyzing, interpreting, and generating content. The feeling of a single unified narrative, the sense of a continuous I, is not a fundamental truth but rather an emergent property, an after-the-fact illusion woven from this multitude of disparate processes. It is a story your brain tells itself and continually rewrites to create the impression of a stable self, much like a constantly updated news report compiled from countless independent sources. The profound fragility of this constructed self-perception becomes chillingly apparent in certain neurological conditions. Take anosognosia, for instance. Patients suffering from this condition, often due to brain damage, can be profoundly paralyzed on one side of their body, yet vehemently deny their paralysis. They will confidently claim they can move their limbs, even offer elaborate, nonsensical explanations for why they are not moving, all while completely unable to do so. Their conscious interpreter is so powerful, so committed to maintaining a coherent narrative of self, that it actively discards overwhelming sensory evidence to preserve the illusion of wholeness. It is a stark, almost terrifying demonstration of how our self-perception is not a direct reflection of reality, but a carefully curated, constantly edited story. This brings us back to the heart of quantum immortality, a concept that hinges entirely on the continuous existence of a singular observer who always finds themselves on a timeline of survival. But if the observer is not a fixed fundamental entity, if this continuous thread of I is merely the greatest illusion of all, a constantly rewritten narrative, a fleeting pattern of neural activity rather than an immutable soul, then what happens to the very foundation of quantum immortality? If you are less like a solid, unyielding diamond and more like a shimmering, ever-changing ripple on the surface of a vast ocean, can that ripple truly persist across infinitely branching cosmic streams? If the observer is not a single point, but a dynamic, ephemeral pattern, then the bold promise of quantum immortality begins to crumble, revealing a far more nuanced and perhaps more unsettling reality about our own existence. What if the very essence of you, your thoughts, your memories, your unique perspective, isn't flesh and blood, but something far more abstract, something akin to data? This radical idea challenges our most fundamental assumptions about life, death, and even the possibility of quantum immortality. Our journey into this mind-bending concept begins in the year 1948 with a groundbreaking paper titled A Mathematical Theory of Communication, penned by the American mathematician Claude Shannon. Shannon's work didn't just lay the foundation for the digital age, it offered a revolutionary new lens through which to view reality itself. For Shannon, information was the resolution of uncertainty. The more choices available, the more information was conveyed when one choice was made. In this view, a living being, and specifically its consciousness, is not some ethereal, indefinable soul, but an extraordinarily complex and precise arrangement of information. Think of it, your brain, a dense network of roughly 86 billion neurons, each capable of firing, connecting, and creating intricate patterns. These patterns, these states of electrical and chemical activity, are a vast, dynamic data set, constantly updating, constantly interacting. This dataset, this pattern encoded in the very structure and state of your neural connections is, in essence, you. From this perspective, the terrifying finality of death takes on a new, stark meaning. It isn't merely the cessation of bodily functions, but the process of that incredibly complex and specific dataset being corrupted, scrambled, and ultimately erased. This isn't some mystical event. It is the inexorable march of the second law of thermodynamics. This fundamental law states that in any closed system, entropy, the measure of disorder or randomness, always increases over time. Life, in this scientific framing, is a temporary, highly localized island of low entropy, an intricate, ordered arrangement of high information, existing within a universe that relentlessly tends towards maximum disorder. As time wears on, as biological systems degrade, the information that constitutes your unique self slowly succumbs to the cosmic tide of chaos, dissolving into the background noise of the universe. It is the ultimate hard drive crash, where the data itself becomes unreadable, irrecoverable. This raises a profoundly fascinating and unsettling question for the concept of quantum immortality. When the universe branches with every quantum interaction, what happens to the information that constitutes the observer? Does the many worlds interpretation imply a cosmic data duplication event at every single quantum choice? Is your unique informational pattern replicated across an infinite number of newly formed universes, each identical to the original at the moment of the split, yet destined to diverge? The implications resonate deeply with the insights of physicists like John Archibald Wheeler, who famously coined the phrase, "it from bit." This radical concept suggests that the physical world itself, all matter and energy, might fundamentally emerge from information. If the universe is built from bits of information, and consciousness is a highly complex arrangement of those bits, then the notion of survival across branching realities isn't about the persistence of a physical body, but about the preservation, integrity, and replication of a specific informational pattern. If consciousness is, as some cognitive scientists propose, a computational process running on intricate neural hardware, then surviving a catastrophe isn't about flesh and blood enduring a physical impact, but about the preservation of the running software, the continuation of the program. This redefinition transforms immortality from a question of biological endurance into a mind-bending problem of cosmic information storage, integrity, and replication. If you are data, then death is data loss, and immortality becomes a question of how that data could possibly persist, perfectly intact, across the infinite branching pathways of the multiverse, a cosmic hard drive constantly making countless copies of itself. Look around you. Every star, every planet, every living cell, and indeed every conscious thought exists because the universe itself seems to possess an almost impossible hospitality. We stand upon a precipice of cosmic improbability, our very existence a statistical anomaly so profound it challenges our deepest intuitions about reality. This isn't mere chance. It is a fundamental observation at the heart of modern cosmology, one that bears an unsettling resemblance to the personal persistence suggested by quantum immortality. Theoretical physicist Brandon Carter, in 1973, articulated this startling observation as the anthropic principle. He noted that the fundamental constants of our universe, Parameters like the precise strength of gravity, the exact charge of an electron, or the incredibly delicate expansion rate of space appear to be exquisitely fine-tuned for the emergence of life. If the strength of the strong nuclear force which binds atomic nuclei together were just a few % weaker, no stable elements heavier than hydrogen could ever form, rendering chemistry and therefore life impossible. If the cosmological constant, the elusive energy of empty space, were off by a margin as small as 1 part in 10 to the power of 120, the universe would either have collapsed back on itself immediately after the Big Bang, or expanded too rapidly for any stars or galaxies to ever coalesce. This is a level of precision that defies casual explanation, like a dart thrown from across the galaxy landing squarely on a single atom. This cosmic precision presents a profound puzzle. Did we simply win an unfathomably improbable lottery, a 1 in a trillion chance that just happened to hit the jackpot, or is there a deeper, perhaps more unsettling, explanation for this apparent cosmic benevolence? The many worlds interpretation of quantum mechanics, which we have previously explored, offers a compelling, if deeply unsettling, answer to this cosmic riddle. It posits that our universe is not unique, but merely one branch within an unimaginably vast multiverse, an infinite cosmic tapestry where every possible combination of physical laws and constants is instantiated in its own separate reality. Within this grand, branching cosmic tree, each universe plays out its existence according to its unique set of foundational rules. In this boundless multiverse, there are countless universes where gravity is too strong or too weak, where electrons are too massive, or where space expands at a rate that suffocates any chance of complexity. In these countless other realities, no stars ignite, no planets form, and certainly no conscious observers ever arise to ponder their existence. The many worlds interpretation suggests that we simply find ourselves in one of the vanishingly rare universes where observers can exist because, by definition, we could not possibly exist to observe the others. This is survivorship bias elevated to the grandest possible scale, an echo of Abraham Wald's bomber planes, where we only perceive the universes that are hospitable to our existence, oblivious to the countless cosmic failures. This cosmic perspective further introduces a chilling concept, the Great Filter. This term, brought into popular discussion by economist Robin Hanson and philosopher Nick Bostrom, posits that there may be some evolutionary or technological barrier, an incredibly difficult hurdle that life must overcome on its journey to becoming a spacefaring, interstellar civilization. This filter represents a universal bottleneck, a point in the development of intelligent life that is so challenging that few, if any, civilizations manage to pass it. Its existence offers another lens through which to view our improbable cosmic luck. The unsettling question then becomes, where does humanity stand in relation to this great filter? Does our improbable existence, the fact that we are here at all, mean that we have already passed this monumental barrier, perhaps an early stage of life's emergence, or the improbable jump from single-celled organisms to complex consciousness? Or, and this is the truly terrifying prospect, does the great filter lie terrifyingly ahead of us, an existential challenge such as self-destruction through advanced technology, a catastrophic climate shift, or an unstoppable cosmic event that awaits us in the future? This second possibility would make our current improbable existence an even more profound statistical anomaly, mirroring the very logic of the many worlds interpretation, where our seemingly miraculous survival is merely a momentary snapshot before an inevitable universal branching toward oblivion. What if humanity's oldest dream, the fervent wish for eternal life, twisted into its most profound nightmare? We have explored the astonishing concept of quantum immortality, the idea that in a branching multiverse, your consciousness might eternally persist, always finding itself on a timeline of survival. It sounds like the ultimate escape from the greatest fear, annihilation. But delve deeper into its chilling logic, and this comforting fantasy shatters, revealing a fate far more terrifying than any end. True quantum immortality, as theorized by physicists like Max Tegmark, doesn't grant immunity from suffering. It merely guarantees you will never subjectively experience your own death. To grasp this terrifying distinction, consider a thought experiment often called quantum suicide. Picture a machine, perhaps a sophisticated device linked to a quantum event, like the decay of a single radioactive atom. This device is configured to have a 50% chance of instantly ending your life. If the atom decays, a fatal mechanism activates. If it doesn't, you survive, unharmed. In a single unified reality, the outcome is simple. You either live or you die. But in the many worlds interpretation, the universe branches at every quantum measurement. So, when the machine fires, the universe splits. In one branch, the atom decays, and a version of you ceases to exist. In the other, the atom does not decay, and you continue to live. The horrifying consequence of quantum immortality is that you, the subjective observer, would only ever experience the click of the empty chamber. Again and again, through countless iterations of this morbid game, you would always find yourself in the branch where you survived. You would be immune to the gun, yes, but only in the most chilling sense, because all the versions of you that perished simply ceased to be your subjective experience. But what happens when the catastrophe is not instantaneous, not a swift, merciful end, but a slow, agonizing descent into a colder hell? You are the eternal survivor. A global pandemic sweeps across the planet, erasing 99.9% of the population, leaving cities silent, choked with dust. Your parents, your siblings, your friends, your children, all gone, their timelines diverging into oblivion. But you remain, utterly alone, navigating a desolate world. Quantum immortality offers no solace from the crushing weight of grief, from the unbearable loneliness of being the last sentient echo in a universe that has moved on without your loved ones. And what of the inevitable internal catastrophes? The human body is a marvel of biological engineering, yet it is profoundly fragile, subject to the relentless march of time. Quantum immortality grants no reprieve from aging. You would live through the slow, agonizing decay of your own body, witnessing the erosion of your physical and mental faculties. Imagine the onset of an incurable, debilitating disease, every cell betraying you, every nerve alight with pain, every memory beginning to fray. Yet, death, the release, would never come. Your subjective experience would remain tethered to the decaying vessel, unable to escape its inevitable biological fate, always finding yourself in the branch where your heart continued to beat, where your lungs continued their labored rhythm, even as your essence withered. The ultimate horror, however, transcends the personal. It stretches across astronomical timescales, reaching to the very end of everything. You would witness the heat death of the universe. Over trillions upon trillions of years, stars would exhaust their fuel, dying into white dwarfs, neutron stars, and black holes. Galaxies would drift apart, driven by the universe's ceaseless expansion, becoming ever more isolated. Black holes themselves would eventually evaporate over timescales so vast they defy comprehension, longer than the current age of the universe multiplied by 1,000,000,000,000,000. The cosmic background radiation would fade to an imperceptible whisper, approaching absolute 0 Kelvin, a frigid emptiness where no energy can be exchanged, no processes can occur. In this cold, empty eternity, your mind, if it could even still be considered a mind, would be ravaged. Ravaged by cosmic radiation, by the unyielding forces of entropy, by the sheer, unendurable monotony of nothingness. Your neural pathways, the intricate network that once housed your consciousness, would slowly succumb to the ultimate disorder, descending into an unbreakable, eternal madness. The myth of Tithonus, the mortal granted eternal life by the goddess Eos, but not eternal youth, condemned to wither forever, becomes a quaint bedtime story compared to this quantum reality. His agony was limited to a human lifespan, to the scale of a single star's existence. Yours would be boundless, an unending nightmare in the dark, silent depths of cosmic time. The true horror of quantum immortality is not that it might be false. It is the chilling, existential dread that it might be true, sentencing the survivor to a fate infinitely worse than a simple, clean end. We have journeyed through the mind-bending implications of a universe where every quantum decision splinters reality, a cosmic tapestry woven from infinite possibilities. The allure of the many worlds interpretation is undeniable, offering an elegant solution to quantum paradoxes and even hinting at a form of quantum immortality. But science, at its heart, is a discipline of relentless skepticism, a tireless search for cracks in even the most beautiful theories. And when we apply that rigorous scrutiny to the many worlds interpretation, significant fissures begin to appear, challenges so profound that they prevent most physicists from embracing this dazzling vision of an infinite cosmos. The first and arguably most significant of these challenges is known as the measure problem. The many worlds interpretation postulates that every single quantum outcome, no matter how improbable, is realized in its own separate universe. If that is truly the case, if every possibility becomes a concrete reality somewhere, then why do we, the observers, still experience the world in terms of probabilities? Why does the universe seem to follow the precise statistical predictions of the Born rule, one of the most fundamental laws of quantum mechanics? The Born rule dictates the likelihood of various outcomes in a quantum experiment with uncanny accuracy. For instance, if a quantum event has a 90% chance of producing outcome A and a 10% chance of producing outcome B, our experience consistently aligns with these percentages. We almost always find ourselves in worlds where the 90% outcome occurred, not the 10% one. But if all worlds are equally real, why don't we find ourselves in the wildly improbable worlds just as often? Consider the flip of a quantum coin. According to WWII, when that coin is flipped, the universe splits into two branches, one where it lands heads and one where it lands tails. Each is equally real. Now imagine a far more complex scenario, a quantum event with a 1 in a million chance of producing a catastrophic explosion and a 999,999 in a million chance of producing nothing. In MWI, both outcomes happen. Yet, we would subjectively expect to almost certainly find ourselves in the peaceful, non-exploding world. The measure problem asks, what is it about our subjective experience, our sense of self, navigating these branches, that always seems to favor the most probable outcomes, effectively weighting our experience according to the Born rule? It is as if our consciousness has a cosmic preference for the mainstream branches, ignoring the countless realities where extremely rare events occurred. This remains one of the most vexing questions for proponents of many worlds. Then there is the subtle, yet equally crucial, preferred basis problem. If the universe is constantly branching, what defines the exact moment and the precise way in which it splits? Why does a quantum system, initially existing in a hazy superposition of possibilities, resolve into distinct, observable states like a cat being either definitively alive or definitively dead? Why doesn't the universe split into far more bizarre and entangled superpositions where the cat is somehow both alive and dead in a single branch, or where its aliveness is inextricably linked to the color of the scientist's socks? Our everyday experience shows us a world composed of distinct classical properties. Atoms are either here or there, electrons spin up or spin down. The universe doesn't seem to continuously branch into infinitely complex, unobservable quantum states that remain mixed up. The preferred basis problem seeks to understand why the universe chooses to decohere and split along these specific, seemingly classical lines, creating the clear-cut realities we observe, rather than a continuous, amorphous quantum blur. These challenges have led many physicists to explore alternative interpretations of quantum mechanics, theories that attempt to solve the mysteries without invoking an infinite number of parallel universes. One such interpretation is cubism, or quantum Bayesianism, championed by physicists like Christopher Fuchs and David Mermin. Cubism takes a radical approach, suggesting that quantum states are not objective descriptions of reality itself, but rather represent an observer's subjective degree of belief about the outcomes of measurements. For a cubist, the collapse of the wave function is not a physical event in the universe, but simply an update in an observer's knowledge after they have performed a measurement. It is less about what is objectively out there and more about what we can know and predict. This view bypasses the measure problem by removing the objective reality of the infinite branches, and it avoids the preferred basis problem by focusing on the observer's information. Another compelling, though often overlooked, alternative is David Bohm's deterministic pilot wave theory, first proposed in 1952. Unlike many worlds or Copenhagen, Bohmian mechanics posits the existence of hidden variables, an actual, objective reality where particles always have definite positions, guided by a pilot wave that influences their motion. This wave, which obeys the Schrödinger equation, guides particles along predictable paths, even when they appear to behave randomly. There is no wave function collapse, and crucially, no branching of universes. All outcomes are already predetermined by these hidden variables, even if we cannot access them. This offers a deterministic view of quantum mechanics, a world where the apparent randomness is merely a reflection of our ignorance of the underlying guiding wave. In Bohm's universe, there is only one reality, constantly evolving, with no need for infinite cosmic copies. These competing interpretations highlight the profound and ongoing debate at the heart of quantum physics. While the many worlds interpretation offers a strikingly elegant mathematical solution to some of quantum mechanics' deepest paradoxes, its philosophical costs and the persistent problems of measure and preferred basis mean it is far from the only, or even the most accepted, solution to the quantum mystery. The universe, it seems, holds its secrets close, and the quest to understand its true nature continues to drive scientists down many branching paths of inquiry, each with its own compelling logic and its own set of profound challenges. The human mind, in its relentless quest for meaning, has often wrestled with the ultimate boundary, the end of existence. For millennia, we have looked to philosophy, to faith, and increasingly to science, hoping to find a hint, a whisper, of what lies beyond. This deep-seated inquiry, often unspoken, shapes our every fear and aspiration. But what if the profound question of quantum immortality was never truly about finding a pathway to an endless future, but rather a powerful, almost alchemical tool designed to reshape our understanding of the present, of ourselves, and of the very fabric of reality? Our journey through the improbable landscape of existence began not in the quantum realm, but amidst the gritty life-or-death decisions of a global conflict. We saw how the subtle distortion of survivorship bias, a cognitive illusion where success stories eclipse the countless failures, led military strategists to protect the most vulnerable parts of their aircraft. This same insidious bias, we now understand, colors our individual perceptions, making our very survival feel miraculously special, a testament to skill or fortune rather than the relentless pruning of probability. The thought experiment of quantum immortality, in its purest form, reveals this bias on a personal scale, suggesting we only ever perceive the branches where we survive, transforming improbable luck into subjective inevitability. It acts as a disquieting mirror, reflecting our deepest anxieties about mortality and the inherent human tendency to narrate our own triumph. Consider the very core of what we call you, that continuous, unified sense of I that narrates your life, remembers your past, and anticipates your future. This deeply cherished self we have discovered may be a far more fragile construct than we dare to imagine. Neuroscience, peering into the intricate workings of the brain, particularly through the groundbreaking split-brain experiments of scientists like Roger Sperry and Michael Gazzaniga, has revealed that our consciousness is not a single, immutable entity. Instead, it is a complex, often fragmented process, with a masterful interpreter in the left hemisphere tirelessly weaving a coherent narrative, even from disjointed or contradictory information. This suggests that our feeling of singular selfhood is not a fundamental truth of the universe, but rather an elegantly fabricated story, a constantly rewritten script that our brain tells itself to maintain a sense of continuity. The continuous observer, upon which quantum immortality hinges, might indeed be the greatest illusion of all, a shimmering, ephemeral pattern, rather than an unyielding anchor in the branching cosmos. Delve deeper, and the very concepts of life and death transform, speaking a stark, unforgiving language derived from the realm of information theory and thermodynamics. Pioneered by minds like Claude Shannon and Ludwig Boltzmann, this perspective reframes consciousness not as an ethereal soul, but as an extraordinarily intricate and specific arrangement of information. Your unique thoughts, memories, and experiences are, in this view, a vast, dynamic dataset encoded within the billions of neurons in your brain. Death, then, becomes the inevitable corruption and erasure of this precious data, an unyielding march towards maximum disorder, dictated by the second law of thermodynamics. Life, by this measure, is a temporary, localized pocket of incredibly low entropy, a highly ordered, complex information structure, existing against the universe's relentless drive towards chaos. The question of survival across quantum branches, therefore, becomes a mind-bending problem of cosmic data duplication and integrity, where your informational pattern must somehow replicate perfectly across countless newly formed realities. And zoom out further still, to the grandest possible scale, and the logic of quantum immortality finds an astonishing parallel in the very existence of our universe. The anthropic principle, articulated by physicists such as Brandon Carter, highlights the almost miraculous fine-tuning of cosmic constants. The precise strength of gravity, the exact mass of an electron, the delicate expansion rate of space, if any of these values were even infinitesimally different, stars, planets, and conscious observers like us could never have emerged. Our universe appears to be an impossible win in a cosmic lottery. The many worlds interpretation in its most expansive form offers a compelling answer. Perhaps an infinite multiverse exists, each with different physical laws, and we simply find ourselves in one of the vanishingly rare realities where observers can exist because, by definition, we could not exist to observe the others. Our personal, subjective experience, intertwined with the very fabric of physical laws, suggests that our existence is a localized expression of this grand cosmic selection, a form of universal survivorship bias. So, the ultimate takeaway from this profound thought experiment is not a simple yes or no answer to our deepest question about mortality. Instead, it is the profound realization that quantum immortality serves as one of the most potent intellectual tools at our disposal. It acts as a catalyst, forcing us to confront the profound fragility of our self-perception, challenging the very notion of a continuous I. It compels us to redefine life and death in the stark, uncompromising terms of information and entropy, stripping away sentimental illusions to reveal a deeper, more fundamental reality. And most importantly, it connects our intimate, subjective experience to the most grand and sweeping questions of cosmology, revealing how our individual existence might be inextricably woven into the universe's most fundamental laws. This extraordinary thought experiment offers no promise of an endless future, no escape from the ultimate boundary. But what it does provide is something arguably more valuable, a unique, breathtaking, and deeply humbling perspective on the improbable, precious, and profoundly mysterious nature of a single, finite lifetime.